Okay, so for this last shape, we're dealing with regular polygons. Remember, regular polygons could have any number of sides, anywhere as low as 3 to make a triangle, and we can go up to, a million sides if we wanted to. So what makes a regular polygon regular? Remember, regular polygons are both equal angular and equilateral. Okay, so when we're dealing with the regular polygon, you need to know it's regular, or remember you'll see the markings. All the angles are the same, all the sides are the same. So what we want to do is we want to talk about some different parts of this regular polygon before we go into how do we actually calculate area. So a regular polygon, kind of like a circle, will have some center point, C. So what makes it the center is that it is the same distance away from every vertex. So for example, if I draw a distance from C to, let's call this A, and then a length from C to, let's call that vertex B, these are the same. So that's what makes C the center. All right, so just writing that down again, C is equidistant to each vertex. So kind of like the center of the circle, and each of these lengths, like C to A, C to B, and C to any of those other vertices, are almost like a radius, but not, the same thing as a radius of a circle, because that's equidistant to every point on the circle. But that's kind of drawing a parallel there. And then what we want to do now is we want to introduce a new idea. And this segment is what we call an apothem. And it goes from the center and is perpendicular to the base. So if you kind of look at this as a triangle ACB, this apothem, which I'm going to call little a here, is basically the height of that triangle going to the base AB. So I don't know where they got the word apothem from, but the apothem is a perpendicular length from the center to a side. And what it actually does, which is really cool, is if you see this triangle ACB, it's isosceles. If we draw the height down that way, it's going to bisect AB. So we get two congruent right triangles, right? And that's using basically the converse of our perpendicular bisector theorem as well. Okay, so that apothem is basically the same idea as a height if we cut out that little triangle from our regular polygon. Then what we want to talk about next is the lengths AC and BC create what we call a central angle. So if we look at angle ACB right here, it's an angle with the vertex C at the center, and the legs go out to two different vertices of the polygon. So the two corners of this regular polygon. So this angle ACB is what we call a central angle. And what's cool about this is if you imagine, and I will just draw this really quick, I have a whole bunch of central angles, right? So I can keep going and connect all these central angles, and you'll see, wait a minute, it becomes a circle. So the measure of your central angle, and I guess I shouldn't write ACB, so the measure of any central angle is just 360 divided by the number of sides or angles. Because if you think about it, all of those central angles will come together to make one lovely circle, which adds up to 360. So that's cool about the central angle. Okay, so I'm just going to erase these extra marks because we're not going to need all of the central angles. We just need one of them. So how does this all come together to give us the area formula for a regular polygon? Well, remember, this regular polygon, all sides and angles are the same. So if I just look at this one triangle ACB, I could replicate it and create a whole bunch of congruent triangles. So basically, to find the area of the regular polygon, I find the area of one triangle and multiply it by how many congruent triangles are in there. So we just basically look at how many central angles we have. 1, 2, 3, 4, 5, 6. That happens to match up with the number of sides of your shape, which then also tells us, wait, all 6 sides is the perimeter. So if the area formula for a triangle is 1/2 base times height, and I have 6 of the same bases, the area sorry for the messy handwriting, polygon is 1/2 apothem times perimeter. I'll write that P a little bit closer, where A is the apothem and P is the perimeter. And again, it just kind of makes sense because we have 1/2 base times height was the area of the triangle. So if you look at just triangle ACB, the height is A, the apothem. The base is the side AB. So 1/2 of AB times the apothem. Now I have 6 of those with the exact same base. So each base, if I add up all 6 bases, it becomes the perimeter. So that's where the perimeter comes from. And all the heights are the same. So it's 1/2 times the apothem times the 6 different bases to give us 6 triangles for this particular case, and that gives us the area of the regular polygon. And again, it doesn't have to be 6 sides. It can be 3 sides. It could be 12 sides. It could be 200 sides. It's the same formula. So what we're basically doing is trying to come up with the height of that triangle for the apothem, or use that height of the triangle. Now, depending on the problem, you could be given different things. So it's really nice if we look at this example A, when we have everything we need. So remember to look carefully at the directions. It says, hey, we're working with a regular polygon. I want to find the area. So let me pull up my formula. Area is 1/2 apothem times perimeter. Then I want to look at my diagram and say, what does it tell me? Well, I know the apothem is 3 because I see this right angle coming down from the center, right, to the side. So 3 is my apothem. 6 is my side length, so I can use that to find the perimeter, right? Perimeter is 1, 2, 3, 4, 5 sides times 6, which is 30. And my apothem is 3. So this is the best type of problem we can get where we have all the information we need. So we just plug it in. 1/2 of 3 times 30. So area is 1/2 of 90, or 45. And again, don't forget your units, square centimeters. Okay. Now, straightforward, pretty easy, not always very fun to do. So I think it's more interesting and more fun to do problems where we're missing information. And you could be missing anything. You could be given, like what we're doing here in part B, you could be given the side length, but not the apothem, and we have to find the apothem. I could give you the opposite. I can give you the apothem, but you have to find the side length. I could also give you this, it's not exactly the radius, but that kind of length this way. I could give you this and say that's 2 feet and ask you to find the apothem and the side length. So there's lots of different versions of this question you could be asked, and you want to be able to think about how to find the missing information. And how do you think we do that? Well, remember, we're going to create triangles, and that apothem creates a lovely right triangle. So we might rely on some trig, or actually we will rely on some trig for this. So again, looking at the directions, area of the regular polygon. So I know I'm looking for 1/2 apothem times perimeter. Perimeter is each side length times the number of sides, so 2 times 6, which is 12. But I'm stuck because I'm like, wait, no apothem. How do we do it? So that's where we have to think triangles. So if I draw in my center and bring down the apothem, here's my apothem, right? I know the entire side length, this is 2. That never changes. And we said, wait, the apothem divides that side into 2 congruent parts. So each of these are 1 and 1, right? And then I could draw in this extra distance from the center to the corner to create this right triangle. So that's a side length of 1. There's my apothem. But we're still stuck because they're like, wait, I can't do SOHCAHTOA with the 90. I don't have enough for Pythagorean theorem, so what do we do? And that's where we think, wait a minute, central angle, right? I can think about this entire central angle by doing 360 divided by 6, which gives me 60 degrees. Now remember, because the apothem cuts that isosceles triangle in yellow into 2 congruent parts, this angle now at the top is half of 60 degrees, half of the central angle, which is 30. So now we have a 30, 60, 90 triangle, but not all of these are going to be special right triangles. So if you're looking at this in general, what can we do? 30 degrees is my anchor. 1 here is opposite. The A is my adjacent. So in this particular problem, we're doing tangent, right? It changes depending on what you're given. So you can imagine if I gave you the hypotenuse instead and asked you to find the apothem and half the side, we'd be doing sine and cosine, all right? So you definitely want to try those out when you get to the practice for this. So moving back, let's go ahead and solve for A. So I'm doing tangent of 30 equals opposite over adjacent. And since this happens to be a special right triangle, which remember isn't always going to be the case, but since it happens to be a special right triangle, you can totally use your special right triangle. Or because my final answer isn't going to B, whatever A is, I'm going to leave it in terms of tangent. So I'm going to make this a proportion. A times tangent 30 equals 1. So A equals 1 over tangent 30. And I forgot to adjust my directions. Let me come back here and let's round to the nearest 10th. Okay, and remember, we don't want to round now. We round once at the very end. So now that I have my apothem, I'm just going to plug it all in. So area is 1/2 of 1 over tangent 30 times 12. Okay, so if your calculator can do this all in one go, go ahead and put it into your calculator. If not, do it one at a time. I might start with 1 divided by tangent 30 to get that out of the way, then times 12, and then times 1/2. Remember, your calculator needs to be in degrees, otherwise you're going to get the wrong value for tangent 30. So if I put that all into my calculator, rounding to the nearest 10th, I'm getting 10.4, don't forget your units, square feet. So when you're practicing this, please practice the different types of regular polygons. And when I say different types, I don't mean like the different number of side lengths. I mean the different types of problems where you're given different information. So I've only done one example here where I gave you the side length. Make sure you try the one where you're given the apothem. Right? What if I said 2 was A instead? How does that affect you? How does that affect finding the side length, which is 1/2, right? Or 2 times the bottom of this right triangle. What if I gave you that kind of radius measurement? How would you use sine and cosine to find the 2 missing values, right? Because we don't want to think it's impossible because it doesn't look like the example, because it's all possible as long as we have one measurement for the regular polygon, which I think makes it more fun to think about. All right, thanks for listening.